Hi, welcome back to the shop. Today we start a new project on the lathe, my 9x20 lathe, and I want to change something that's bugging me for a long time, and it's the cross slide crank and the spindle and the bearing block for the crank, and also the graduated ring. So let's take a closer look and talk what bugs me. Okay, this is the cross slide crank, and I really don't like this design very much. First of all, I don't like the crank, which I made, so I can only blame myself for this. I don't like the fact that it's a crank. I prefer the ball handle style, like on my engraving machine, and we will make one of these ball handles instead of this crank. I don't like the internals of this. There are two axial bearings, axial ball bearings, and no radial bearing. So while it can take a lot of thrust and push and pull wise, it's really bad on radial stability, and that results in a real crappy feeling when you crank this. When you crank the cross slide, it feels like cheap. It's really cheap. I will machine this part here. Will be completely made new. We will machine a new bearing block with two angular contact bearings, and we will make a new, bigger graduated ring and a vernier on the other side, so you can do really close reading, and we'll machine a ball handle just to make it nicer. And all of this is inspired by George H. Thomas, which might be a name some of you might be familiar because of his books, the Workshop Manual and the Workshop Techniques books. These are some of the finest books ever written on model engineering and model or home shop tooling. So if you don't know the books or don't have them, run out and buy them. Best books. And yeah, this is what we're going to do, and I already did some sketches, so let's go to the bench and look at that. This time I did not only make hand sketches, I made a proper hand draw. Start with the bearing block, of course, which we'll machine out of this piece of free cutting mild steel. All of this will be machined out of steel just because I have it. I will do a lot of turning work off camera because you have seen this 100 times. The more interesting parts I will show on camera. Okay, I checked up a slug of free cutting mild steel, and I machined the first side to diameter and faced it. And you might notice the surface finish on here. A lot of people shoot for the glossy, high shine finish on the lathe, and in my mind that's a two-sided sword. A high gloss finish doesn't mean precision in the same sentence. If you do turning and milling, high gloss means normally that you're using a tool that introduces a lot of pressure and rubs and smears the surface shiny. If you use a tool that's super sharp, you get this gloss finish. This is super smooth, and this is really I would use this as a bearing seat from the surface finish, and I will not take any emery cloth or something like that to it. This is really a nice surface, and I prefer this over a scratched glossy finish. And I will take this piece out. I chamfered it, of course, as you do. We'll take it out and turn it around. and we're going to use some brass shim stock to protect our part. First we close down the chuck as far as we need it, and we leave some wiggle room. Now we can insert our, this is 0.1mm brass shim stock, and I showed this a few times here on the channel. I have a spool of this stuff in the shop exactly for the purpose of protecting surfaces. The 0.1mm stuff is thin enough so you can cut it just with regular household shears or snips, whatever you want to call these, scissors, but thick enough to protect surfaces, and also it's thin enough and precise enough not to mess up your precision. But still you can quite get a good bite on your part using the brass shim stock. And I need some surface here so I can indicate the part in. So let's clamp it, and we can reef down on this pretty good. And this is not going to run true, but we're going to indicate and set it to run true. Okay, I have my dial test indicator here, and you can see that we have about 0.1mm run out. And now I loosen my mounting bolts for the chuck, and I have some wiggle room in there. And I take my plastic hammer, and now we can bump this part to run true. Yeah, that was a bit much. Oops. And you tend to overshoot slightly when you okay, this is within 1/100th of a millimeter. The rest is surface noise from the surface. Yeah, this is about 1/100th of a millimeter, 1 or 200. Yeah, 1.5 of a millimeter. So this is now set up, and we can proceed on. Okay, we want the step where the vernier ring runs on to be 50 millimeters, pretty exactly. And we're going to measure this. And we have 52.05 millimeters, so we have 2.05 to go. And just do a quick idiot check with the calipers. 52, because it's pretty easy to overshoot by 1 revolution on the drum of the micrometer. And we undercut the rear edge slightly by plunging in with the tool. So when we machine the rings, it seats nicely into the corner and doesn't ride on the edge. Don't like this. I can just be sure. In fact, this measurement isn't really critical because we will machine the mating part anyway. Yeah, we hit 50.02 millimeters. This is an 18 millimeter annular cutter or rotor broach, and we're going to use this to punch start a hole through this piece of metal. So there we go. We went through one time and there is the slug. Yeah, should have used pliers. And don't touch it because it's hot. There you go. That's the slug. And now we can bore out this hole. Just with a boring. Okay. I turned the first bearing seat off camera, and it's 28.00 when measured, or slightly minus, and I have my bearing here, and it's a very close fit. I could push it in, and I don't get it out right now, but I will have to unclamp this part right now anyway. But you see where we are right now, and now we flip it around and we will machine the second bearing seat. Okay, I flipped the part around. I have again brass shim stock in between the jaws and the part, and the dial test indicator. Wait a second, I will rearrange it so you can see the dial. That's about 1/100th of a millimeter runout, and that's perfectly fine for what we're going to do. I butted it up against the face of the chuck so it doesn't wobble in axial direction, and just to be sure, the runout on the face is also almost zero. And now we can machine the second bearing seat. Okay. I have a 12mm CCMT 0602 boring bar, Mitsubishi boring bar in the tool holder, and now we're going to machine this to 28mm, 13.5mm deep. I have my depth stop on bed set to that depth, and we can go. Okay. I almost finished it. We are at 27.73, so we have 2.27 to go. And we will do that in one cut. We will take the cut and do a spring pass, because boring is always a bit, the tool tends to get pushed away, and with the spring pass you take out that spring. And on the last pass, of course, we don't drag out the tool. Yeah, that's why I don't like inserted tooling for close fits. We are 4/100ths of a millimeter shy of the final dimension. Now we have two possibilities. We can go on with the boring bar, possibly overshoot it, get a bore that's too big. We can change to a high-speed steel boring bar and shave off 0.04 of a millimeter. Also very dangerous because you have to touch off. We can take another spring pass, possibly ruining the surface finish, or sit in the corner and cry. Last option is the worst because nothing gets done. Changing to a high-speed tool bit, yeah, I could do that, but we will give the boring bar another shot. We'll take a spring pass, and if it doesn't work out, we still can slightly adjust it. This is a pretty sharp carbide insert, so we might get away with it. Let's try a spring pass. And we made some chips, so this insert is really cutting well. And this is really not how you turn a bearing fit. This sneaking up to the final dimension with a carbide insert is really the worst practice you can do. But yeah, we shaved out about 0.01 of a millimeter. Yeah, we will take a 0.04 millimeter cut with this boring bar. This might have worked. Yes, and we have 28.0. Bit hard to see on camera, but trust me, this is on size. So we saved that one, but really can mess up if this happens. Now we chamfer the edge, so 3-point scraper. And the turning work on this piece is done. Right now we are machining the vernier ring, which will slip over this the smaller diameter. This is 50.02 millimeters, and we're going to bore this to 50.04 or 05 to give it some clearance. So it goes with little play on it, but it's freely to rotate. And I'm using not the carbide inserted boring bar, the index boring bar. I'm using a solid steel boring bar with a small solid carbide cutting bit that I ground myself. And this is on a small lathe superior in cutting performance. I will take a 2mm deep cut that's 4mm in diameter, and you will see that the chips that come off this tool are super nice. I turned the internal diameter to fit the bearing block, and now we're facing the ring off to final thickness. And I'm doing this on a magnetic chuck because I get it's very easy to machine parts very parallel on a magnetic chuck because they are automatically parallel when you face them off. So I measured the height from the ring to the magnetic chuck with the depth mic, and we have 0.42 millimeters to go. So Let's go for it. Yeah, that's right. 10.00. I think that's good enough. Now I'm going to take down the outer diameter to 60 millimeters, almost all the way to the magnetic chuck. Of course, we can't go all the way because I don't want to machine into it, but then we can flip the part around and chamfer the remaining material. We're taking the final cut on the outer diameter down to 60 millimeters, and yeah, let's go. And I went almost all the way to the magnetic chuck, but I have still a small step of material left, and I will just show it to you. Okay, let's take it off the chuck. I have broken this edge with a file. And there we go. You can see this very thin rim of material left. But we will recheck the piece like this on the magnetic chuck, and we will just turn a small radius on this side, and this will remove this. It's almost like a big burr, so we will go and remove this. Okay, this is the bearing block, and this is the vernier ring we will set on here, and this can spin freely. It's a pretty close fit, and it has some friction to it, and it really feels good, and I like it. And later in use there will be one locking screw, some screw with a small knurl, some screw to lock it in place, and on top will be the vernier scale, and here will be the dial be sitting, which will also be adjustable. And the dial, I have the drawing here, side view, is the next part we're going to machine. This is going to be turned also out of free cutting mild steel. We will knurl it, and yeah, it's not much to it. It's a pretty simple part. Okay, right now we're machining the dial, and we're cutting the 45-degree chamfer. Big 45-degree chamfer here. We can't do that with a 45-degree lathe tool because it would chatter because of the long engagement line. For that reason I tilted the top slide to 45 degrees, and we're cutting the taper. Okay, we're going to knurl the front portion of this ring, and I already set up my scissor type knurling tool, and I already slightly tightened it down to see if my if the knurling tool is aligned straight. We're not going to move side to side because the portion we're knurling is smaller than the knurling wheel. Okay, excuse the freehand, but here you can see the portion we're going to knurl, and here is the knurling tool, and you can see that the light imprint from the knurling tool is all across the surface, and that means that our knurling tool is straight, is aligned to the workpiece. So ready to know. Okay, we're going for slow RPM and we're using some soluble oil to lubricate everything. This was a bit of a struggle, but I think we got it. That's 60 millimeters is really the uppermost limit this tool will do. Because at 60 millimeters it's really hard to get it over center, over the spindle center, and then it gets, when you don't have it on spindle center, it gets pushed back. And it might even turn your tool post around if it's not dialed in position, and some other problems. But I'm very happy. I'm very happy. Okay, this is the engraving, and I think it looks pretty good. I need to chamfer this side and redo this radius because some material gets, of course, pushed over. But apart from that, I'm very happy. It was a bit of a struggle to get it on there because of my nerding tool, but apart from that, worked out fine. Okay, we're parting off the final, the finished piece. I'm almost all the way through, and to prevent the part from dropping onto the machine's bed or on the cross slide, denting either the cross slide or the part, I have a drill bit in the tailstock chuck that I'm going to use to catch the part. Not much material left. Hope we don't crash it. There we go. Parting such heavy pieces on such a small lathe is a bit sketchy, but you don't have to take it to the saw. And that's the ring we will graduate later on the engraving machine. Okay, finally I messed it up. I overshot this bore by not 1 or 2 hundredths of a millimeter, I overshot it by 2 millimeters. It should be a 10 millimeter bore, but I machined it to 12 millimeters. So I had a problem. My solution to this is this drill bushing. This is a hardened drill bushing. It has 10 millimeters internal and 15 millimeter on the outside, and this hardening ground. I opened the bore up to 50 millimeter, very close fit, and I'm going to press this drill bushing into the bore and then machine it flush with the part. So it's not a lost cause, because in fact it's even better, because we have, by pressing the hardened drill bushing in, we get a nice ground and hardened bore. Okay, I pressed the drill bushing in from this side, you can see it, and I faced the end off. The drill bushings are only case hardened. Once you're through the outer case hardened layer, they machine pretty good. Yeah, that's the finished dial without the engraving. The engraving will exactly look like my sketch here, and this is the bearing block with the vernier ring, and this will go together like this, and this part will be spun, and this ring here can be adjusted to set 0 if you want to do minor adjustment without moving the actual dial. Okay, and just to show you where it goes on, we pull off the handle. And I really don't like the axle bearings for such a purpose. And this is our bearing block, our new one. We still have to drill the holes to mount it to this hub here, but it will go on like this, with one bearing in front and in back, angular contact bearings, and in front will sit the micrometer drum, and here will be a crank, a ball handle. And I think that looks pretty good. It's nice, big diameter, very solid. The heavy dial will give it some inertia, so it cranks nicely. This crank and dial, they are made out of aluminum, and they have no weight to them. And I like it when you turn a hand wheel and it has some, you feel that there is some mass behind it. And from this I expect this behavior, exactly like I wanted. And this is the bearing, this slips on like this. So yeah, that's where everything will go on. Now we have to put it back together so I can machine the remaining parts. Back together. Yeah, feels like crap still. Ooh. Yeah, something is, I won't bother adjusting this anymore, because this is almost ready to go. So I hope you enjoyed it so far. Next part will be making the remaining parts, and the last part, I think this will be a 3-parter, we will do the actual graduations and the engraving, of course. Thank you for watching. See you next time.